Well, it's taken a little while, but here we are, a complete 3D printed drone. It is ready to fly, but before we go to the flight test, we should cover one major change I've made to the drone since the last video. In that video, I showed off the motors soldered onto small ESCs that easily fitted into the space under the arms. Unfortunately, when I tried to actually use those ESCs during a first test flight, two of them wouldn't respond reliably to speed changes and made the drone keep flipping over as the autopilot lost control. Given that I was always a bit suspicious about how cheap and small they were for their claimed rating of 30 amps, I opted to instead switch to a tried and true 30 amp ESC that I'd already used before. As you can see here, they're a lot bulkier and are not so much inside the arms as just hanging on the bottom, but they're a lot more reliable, and so I'll take that trade-off. You can also see that I've done a distinctly average job of the power distribution wiring, but it does work. It's hard to make it neat without a PCB. Anyway, with that said, let's try and get this thing flying. The first step, after everything is wired up, is a motor test. This verifies that each of the motors and ESCs are working properly, and crucially, they're in the right sequence and spinning the right way. I somehow managed to wire them all correctly on my first try, which, let me tell you, is definitely unusual. After that, the drone needs some calibration, first of its gyros, which you do by placing it on each of its 6 sides, and then of its compass, which involves a fun little dance, holding the drone at various angles for several minutes until it's figured out how to make the compass and the gyros agree. With all of that done though, it's time for the real test. I placed it in the car park here outside the workshop, far away from any vehicles or buildings, and slowly revved up the motors. With the bad ESCs before, this is the point where a fuse started cutting out, and as I tried to pull the aircraft into a low hover, it would instead flip and land upside down. With these new ESCs, however, everything looked smooth, and as I slowly increased the throttle, it rose off of the ground and entered a stable hover. A few control inputs confirmed it was responding well and seemed to have no oscillation at all, really, and then, all of a sudden, the vehicle took control and ended its return to home sequence, rising up 10 meters, moving to its initial takeoff coordinates and then landing rather smoothly. It was quite an unexpected but good demonstration that the fully autonomous mode was working great, but I had an almost fully charged battery in there. So why did it enter the fail-safe return to home mode? Looking at the logs confirmed it was indeed because the battery voltage had dipped too low, from the 16.6 volts it started at to below 14.2 volts, which is a lot of drop for about 20 seconds of flying. I then remembered two important things about the batteries I was using. First of all, they weren't a huge capacity, and the motors on this drone were quite power hungry. Secondly though, on that day, it was a rather brisk -15 Celsius, or 5 Fahrenheit, outside, and lithium polymer batteries really hate the cold. It makes them voltage drop even more. So, what's the answer when one battery isn't enough? 2 batteries. I 3D printed a new double-wide battery sling that hung under the main body, wired in 2 of the same 4S 3.3 amp-hour batteries in parallel, and had another go. This time, the vehicle entered a stable hover with much less voltage drop, and I could get to proper testing. All 3 axes of control seemed to respond well, and the vehicle's climb rate was very decent considering how heavy it was with 2 batteries. Satisfied, I performed a slightly poor landing and called that a great initial test. Honestly, I thought that I would have a series of design iterations after my first test, making the arms stronger, changing the weight distribution, but no, it just worked. There is some credit to the design there, I think, but also a lot of credit to the autopilot software, ArduPilot, for keeping things stable even when they're not perfectly correct. Crucially though, it seems to perform just as well as the original frame it replaced. No oscillation, pretty tight control, it really feels very good. And more importantly, when I crash this one, I can just 3D print some new frame components to replace the broken ones. And let's talk about costs quickly. These motors are $18 each, and the ESCs are $10 each, meaning the total propulsion system here costs about $170. These props are cheap, only $2 a pop each, and so another $12 for those. The autopilot module, GPS, telemetry, and control radios were all ones I had on my previous drone, but if I was going to buy them again, they're worth around $500. These batteries are about $30 each, so $60 for the two I'm now using. The frame, though, even though it's printed in expensive glass fiber reinforced nylon filament, it only costs $30 to print, and it weighs 480 grams, which is the same weight as the frame it replaced. And what I like about the end result here is that the parts most likely to break in a crash are those at the edges of the vehicle, the props, the arms, and the motors, and these are now some of the cheapest and easiest parts to replace. The only hard landing that could get to my expensive avionics in the middle here is an upside down one. And frankly, I'm probably going to design a frame to go over this section as well to give it some protection and a bit of a neater look. So apart from that, what's next for this drone? Well, for me, it's tinkering and playing around with the design, as well as transferring across some ideas I've been trialing on its bigger sibling, this 80 centimeter wide carbon fiber frame that I've built as a medium heavy lifter and payload dropper. For you though, well, I'm pleased to announce that I've uploaded the files of this design so that you can have a go at making your own one. Go look in the video description or the pinned comment to get a link over to that, complete with a list of all the various components I use to build this one and where you can buy them or similar. I will caution you, you need to use a stiff filament to print something like this. Nylon or polyamide, PA as it's often called, is best, especially with glass or carbon fibers as a filler, but you could probably get away with ABS. PLA is as stiff as ABS, but I'd recommend against using that unless you want your drone to melt in a hot car. And PETG is just way too flexible. Definitely avoid that. If you do end up building your own, do let me know. I'd love to see some pictures of other ones out there in the wild and any ideas for modifications or improvements people make. There's also a bunch of other designs you can make with the same basic arms. I suspect both a quadcopter and octocopter would work great. Anyway, I hope you enjoyed this build. I certainly did, even if rewiring and then Christmas interrupted it in the middle. I will of course be back soon building something else impractical, and it's going to be a fun one. See you then.